Hi, and welcome to our second video on proof. And what we're going to do is look at two what's regarded as kind of classic proofs. Now, it might be that you are required to essentially reproduce these things in the exam. So it's one of the few sections of the course where you kind of need to learn them pretty much off by heart. So if you do get asked to do the proof in the exam conditions, that you're able to eventually churn it out. So here we go. Let's first of all have a look at infinitely many primes. Now here's the thing, if you're any kind of a maths nerd, then you'll know that kind of prime numbers are the things that really interest mathematicians, because there's no real pattern to them, and they are essentially the building blocks or the DNA of all mathematics. And what we're going to do is reproduce a proof that is thousands of years old, and it comes from this guy, Euclid of Alexandria. And again, if you're any kind of maths nerd, you'll know all about this fella, but if you're not, let me just briefly tell you about it. He was one of the big So what we're going to do is essentially reproduce a proof that is quite literally thousands of years old, and it's based on the work of this guy, Euclid of Alexandria, like the big granddaddy of mathematics. One, he's up there with Pythagoras and Archimedes as one of the big Greek thinkers and philosophers, but he was, the mathematician. Referred to as the founder of geometry, did a lot of the basic work, which he put together in his book called The Elements. Now, The Elements essentially was a whole series of books that were used for teaching maths right up until like kind of late 19th, early 20th century. And I'll put there a little statement about its estimated entity, second entity to the Bible, number of editions. Just be clear, that's number of editions published, as in how many reprints it's gone through, not actually the number of actual copies. I'm not trying to claim that a mathematical textbook rivals the Bible in terms of the number of copies produced. But, it was a massive, massive deal, and is like the kind of the ultimate in, not the mathematical Bible, if you will. And in one of his books, Euclid proved there are an infinite number of primes. Now, he technically didn't do it by formal contradictions we're going to do, but essentially what we're going to do is basically kind of what he did. And as I said before, this is the first one that we're going to look at, infinitely many primes. There's the other one which is to do with irrational numbers, which we'll come to in a second. So here we go. The conjecture is there are infinitely many primes. Now that seems slightly counterintuitive just for a kickoff, because you must be thinking, well, as numbers get bigger and bigger and bigger, and we get into kind of millions and tens of millions and hundreds of millions, if you think about how many smaller numbers there are than a particular massive number, you got to be thinking at some point there's got to be some other number somewhere that goes into it. Surely you can't end up with these absolutely huge numbers that have no factors. And it turns out you absolutely can, and thank goodness you can, because it turns out internet security is one example of where we use these kind of massive prime numbers. All your financial transactions are protected by algorithms that are built around prime numbers. But that's, I'm kind of getting off topic. That's another conversation to have at some point. But what we're going to do is say, well, here we go. Let's assume our reverse statements are negation, and that's saying there are a finite number of primes. And if there's a finite number of primes, it means we can write them down as a complete list. Might take a long time to do, but we'd be able to write down all this, so you to go 2, 3, 5, 7, 11, 13, and keep going and keep going and keep going and keep going until you've written a complete list. And there's our algebraic version of that complete list. So we've got all our prime, there's our first prime number, second prime number, third prime number, keep going, keep going, keep going, until you've written down all the primes. Now, what we're going to do is take those numbers and say we're going to come up with another number q, and q is going to be the product of all these primes. So we're going to take all these numbers, times them together, but then once we've done that, we're going to add 1. So q is all these numbers times together, and then we're going to make it 1 bigger. We've added 1 onto it. So we've got this absolutely massive number that's q, that is the product of these plus 1, and there it is algebraically. And what we're going to say is that now q has either got to be prime or it's not prime. This number exists, and it's got to be one or the other. So let's just examine that statement in light of our finite number of primes. Let's start off with q is prime. If it turns out q is prime, then we've got a new prime number that was not on our list of primes. So if q was prime, we would have been able to write it down as part of these. Clearly we haven't. So q is another prime number, a bigger one, and so therefore straight away that's a contradiction to our reverse, our negated statement. There's a finite number of primes, because in our original list, where we wrote them all down, we didn't write down q. Okay. Now, if q is not prime, that means it contains a factor, and it must be divisible by some other prime number. It's got to be, because you can take any number. If you go back to when you did prime factors and factor trees and all that kind of stuff, you should know that you can take any number at all and split it down into its kind of basic elements, its DNA, which is the prime numbers. So we're saying if Q is not prime, it must be divisible by some prime number. And I'm going to call that prime number P, and I'm going to give it subscript I. So PI. What we're then going to do is have a bit of thing. So, well, if PI is on our list, so if it is one of these numbers here, that means it's a factor of essentially that times that times that times that, all the way up to Pn, which means it can't be a factor of Q, because if it's a factor of this bit stopping here, it can't be a factor of Q because Q is 1 bigger, and it would mean that 1 would have a factor as well, and PI would be a factor of 1, and we know 1 doesn't have any other factors. So what we've now realised is that if PI is one of these, it can't actually be a factor of Q. Right? So therefore, if Q is not prime and PI exists, it can't be in our list, in which case it's a brand new prime number, and so therefore we've got a contradiction as well, because it's not one of the ones that we wrote down before. We found a new one, so we haven't written them all down when we wrote our original finite list. So if Q is prime, we have a contradiction. If Q is not prime, we have a contradiction. Long story short, contradiction. So therefore there have got to be infinitely many primes, and this is true by contradiction. And if this comes up in the exam, then what you've got to be able to do is just explain essentially what is on this slide at the moment. Now, I mentioned at the start that kind of mathematicians are massively interested in huge prime numbers, and I wouldn't be any kind of a math nerd if I didn't talk very quickly about GIMPS. Now, this is not technically part of the A-level maths course, but it's just something that is worth talking about just briefly. So if you're not interested, turn off, move on, kind of fast forward a bit. If you are interested in GIMPS, great internet Mersenne prime search, then feel free to listen on. So Euclid 2,300 years ago said, yeah, there's definitely infinitely many primes, and there are some absolutely spectacularly large prime numbers. And the main problem you've got, and the reason that the whole internet security thing is built around prime numbers, is there's no simple way for actually determining whether or not a number is prime. So if I gave you a huge number, what you would have to do is literally go through and start doing divide by 2, divide by 3, divide by 4, and so on and so forth, and just keep doing the divisions and seeing if you get remainders, and checking every number to see if you can find a factor. Now, one way of being able to find prime numbers was proposed by a French monk called Mersenne. And he came up with this formula, which is fairly straightforward. It's just powers of 2, then take away 1. And that will generate prime numbers, but it won't always generate prime numbers. So, for example, if we do 2 to the power 5 minus 1, that's 32 minus 1, which is 31. Tick, it works, prime number. But the next one is not a prime number. So sometimes it generates primes, sometimes it doesn't. And what that means is every time you come up with a Mersenne number, i.e. 2 to the power of something, take off 1, it's got to be checked. And to do that check and to go through that laborious process of doing all that division is now done just using basic computing power. But it needs a massive amount of runtime to be able to do it. Even with the most powerful computers, it takes a long, long, long time because we're dealing with absolutely huge numbers. And so that's what GIMPS is. And what GIMPS is essentially, it's an internet-based search, and it's an algorithm that you can download onto your computer, and essentially what's happening is your computer is just doing all the checking in the background while you run other stuff. It's just kind of churning away at particular numbers and trying to find out if they're prime or not. And so it's just running a little program. And the latest Mersenne primes we found was 2018 by an American guy, and it's known as this is 825899331. And the reason it's given that slightly bizarre title is because the value is that. So that is 2 to the power of 82,589,933, and then take off the 1. Now, that doesn't look too bad as it's written there, but when you start thinking about the number of digits that there are in that number, it's actually got 24, like I say, nearly 25 million digits. Okay, and so you can imagine how long it would take and how large a piece of paper you would actually need just to literally write the number down, let alone do any computing or calculations on it. So you can see straight away why it is that these massive prime numbers take so long to find. And like I say, what's his name, Patrick, came up with this one. It is 51st Mersenne prime to be found, so all this kind of computing time has been run, so it's not churning out very many of these things. I think this is the kind of mathematical equivalent of why would you bother climbing a mountain? Because it's there. Why would you bother looking for these things? Because they exist. And after all that hard work, let's say he got himself a monetary prize of around about £3,000, which is, let's face it, not a huge amount, but you know what? It's better than nothing. So there you go. If you are interested at all, then if you just kind of put Great Internet Mersenne Prime Search into Google, I probably wouldn't put GIMPS into Google because you never know what you're going to get, and you can set your computer to running in, who knows, you might be the next person to discover the next prime number. Right, that's done on primes. Let's move on now and let's have a look at irrational numbers. So, irrational numbers. This is the second one that you need to be familiar with, and it's all to do with square roots. Let's just have a quick reminder about irrationality. So, irrational numbers are the numbers on the number line that have got decimal places that just go on and on and on forever without repeating, and they tend to be square roots and things like pi and so on. If you remember back to GCSE, you'll remember taking decimal numbers that go on but have got a pattern. So, for example, 0.2323232323 and so on, and you'll remember you can take that and you can write them as a fraction. So those things are rational, because essentially the definition of a rational number is it can be written in the fraction form p over q. So what we've done is said, if our conjecture says root 2 is irrational, then our negated statement, the reverse, is that root 2 is rational. And if it's rational, it can be written as a fraction. Okay. Now, the other key thing about the fraction is the fact that it's a fraction and it's written in its simplest form, which means you've got no common factors, so you can't do any cancelling. Right, so that's the setup. Let's just have a little look at what we're going to do. So we're going to start off with the statement. We're going to say root 2 is rational. So root 2 can be written in this form here, so that's where I'm going to start. So root 2 can be written as a fraction, where p and q can't be simplified any further. A little bit of rearranging, so I'm going to move the q over, and then I'm going to do some squaring, so we end up there. Now, if you have a look at what's going on with this, if we particularly look at this side over here, what we're saying is that p squared is even, because it's 2 times something, and if p squared is even, so p has got to be even. Now, within this statement here, there's kind of, technically speaking, we should have to go back and prove that this statement is true as well, and that would be another proof by contradiction. But for the purpose of this proof, you can assume that this is correct and doesn't need reproving. Although technically speaking, for a full and complete proof it would do. But for the purpose of this, we're happy to assume that. So what that means is p is even, because obviously 2 times something squared, 2 times anything creates an even number. So that means p is an even number, which means we can write it in that form, and we've mentioned that previously. So what I'm now going to do is take my statement here, and I'm going to rephrase p, so p is an even number. So there we go. And now I'm going to do a little bit of work on this. So we've got 2q squared equals 4m squared. And now what I'm going to do is rearrange this so it says q squared equals, and so we've got q squared equals 2m squared, which again means for some value m, and we know m is an integer, double it, so therefore this thing over here is clearly even, which means that q squared is even. And if q squared is even, q is even, and so can be written as an even number, which is 2n. So there we go. So what we've done now is we've demonstrated that if this statement here is true, that means p and q are both even numbers. So let's just have a look at that and say, well, if we go back to here where it says it's got no common factors, what we're saying here is p and q are both even. So therefore, if they're both even, they could both, like I said, this fraction here, if they're both even, can be divided top and bottom by 2. But our statement said there's no common factors, where clearly we've shown here that if this statement here was true, then there are common factors. And that's where our contradiction is. So we've got a contradiction which says that if root 2 is rational, there's a contradiction, so therefore root 2 must be irrational. Again, that's the standard proof that you just need to be able to crank the handle and churn it out and explain what's going on. The only slight variation to that is you might get someone that says, well, maybe prove that root 3 is irrational, or root 5 is irrational, something of that kind. And essentially in those situations it's exactly the same, but what you'll find is if you use, instead of it being root 2, you get a 3 going on in here, then your common factor will be 3, or if it was root 5 is irrational, your common factor would be 5, and so on and so forth. So this setup will work quite happily for any square root, obviously that's not a square number. So there you go. Those are your 2 proofs. You need to make sure you know them, and so then you can kind of trot them out if they do pop up in the exam. Job done.